A second-order differential equation is one that contains no derivatives higher than second order. For example, first derivatives, second derivatives, but no higher derivatives such as, say, third-order derivatives. This would be a third-order derivative here, d cubed y by dx cubed.
In practice, second-order differential equations cover a very broad range of problems in science and engineering, including most of the simple oscillations and waves that we come across. This makes these second-order equations particularly important and useful. Now, though these are more complicated than the first-order equations, the good news is that because of the way that the physics of many systems works, here we will not need any differential equations beyond second order.
So let's look at a very important example of a second-order differential equation, the simple harmonic oscillator. This equation is of the form d2y by dt squared is equal to minus omega squared y. And for the moment, we're not saying what omega is, but it's some real number, at least for the moment we'll presume that. And so this means that minus omega squared is definitely a negative number, because omega squared must be positive. Now, for this equation, any of these functions, the exponential of I times omega t, the exponential of minus I times omega t, the cosine of omega t, or the sine of omega t, any of these functions is a solution, and you can easily check that. If we think of t as time, these all represent oscillations with what we call the angular frequency omega. We could also have used a frequency in there, omega over 2 pi, but it's more convenient algebraically to use what we call the angular frequency. And the general solutions of this equation, since it's a second-order equation, need two arbitrary constants. So possible general solutions of this equation include y is equal to arbitrary constant a times cos of omega t plus arbitrary constant b times sine of omega t. Or alternatively, we could have y is equal to an arbitrary constant c times the exponential of I omega t plus the arbitrary constant d times the exponential of minus I omega t. Or, for example, we could also have y is equal to the arbitrary constant f times the sine of omega t plus another quantity here, capital phi is what I've written, which we would think of as a phase. And all of these constants, as I said, a and b, or c and d, or f and phi here are arbitrary. And there are other forms we could choose here. We could have used a cosine function in here instead. But any of these solutions here can be written in terms of any other solution. So this solution we could rewrite in terms down here, because we know that the exponential of I omega t and the exponential of minus I omega t can be rewritten using Euler's formula. And it's also possible using trigonometric formulae to write this solution in this form, or indeed a similar form with the cosine in here. All of these solutions are equivalent to one another. Incidentally, with this form here, we can see why we need two arbitrary constants. This first arbitrary constant is telling us the amplitude of the oscillation, how big it is, and the second one, which we typically call the phase, is telling us where the oscillation starts in time, or where it's referred to in time, the position in time of the oscillation. So we need two constants in order to specify an oscillation like that. Just one note here on time derivatives. We encounter time derivatives all the time in mathematics and physics, and as a result there is a shorthand notation we sometimes use, which is to put dots above the variable being differentiated with respect to time. And the number of dots then indicates the order of differentiation. So dA by dt, the first order derivative with respect to time of some variable a, we could write as a with one dot above it. And the second order derivative of the variable a with respect to time, we could write as an A with 2 dots above it. This is sometimes a dangerous notation because sometimes you don't notice the dots. Another example of the same equation but in a different context is what is called the Helmholtz equation. So we use the same mathematics here, but with the second derivative in position, z, instead of time, t. So in that case, we might be writing the same equation, but with just z's instead of t's and a k in here instead of the omega. Equivalently, we can write that in this form, and this is actually a more common form for when we're writing this particular equation, but they're entirely equivalent, of course. And this equation describes oscillations in space z rather than in time t. And it's an example of a wave equation, and we're going to come back to this quite a lot later on, so I won't say a lot more about it here. But it can describe the amplitude of a standing wave on a string. So we'll come back to that later on. But note the mathematics is the same, so we can use the same solutions, but with z instead of t and k instead of omega.